To this end, what we'll talk about today is to discuss linear cost functions and the three common ways in which they behave. Again, think about these when we say linear cost function, what that means moves along a straight line. We're going to explain the importance of causality in estimating cost functions. We'll understand the various methods of cost estimation. We want to outline 6 steps in estimating a cost function using quantitative analysis. We want to describe 3 criteria used to evaluate and choose cost drivers. And finally, we'll also explain nonlinear cost functions, and in particular those arising from learning curve effects. And we want to educate ourselves on what to be aware of with respect to data problems encountered in estimating cost functions. A cost function is a mathematical description of how a cost changes with changes in the level of an activity relating to that cost. And so that is, as activity increases, do costs increase? Do they increase at the same rate? Is there a relationship between the rate at which costs increase with respect to change? And so that's what we're talking about with respect to how changes in cost associated with the level of an activity related to that cost. Managers often estimate cost functions based on 2 assumptions. That's variations in the level of a single activity, that's the cost driver, explaining the variations in the related cost, and cost behavior, which is approximated by a linear cost function within a relevant range. These assumptions are used throughout most, but not all, of this chapter because not all cost functions are linear and can be explained by a single activity, and we'll discuss those later. And so just a little cost terminology again. From prior chapters, we're familiar with the distinction between variable and fixed cost. And in this chapter, we introduce mixed cost. So variable costs are costs that change in proportion or change in total in relation to some chosen activity or output. Fixed costs are those costs that do not change in total in relation to some chosen activity or output. And then we have mixed costs, which are costs that have both fixed and variable components, which are also often referred to as semi-variable cost. And so here we have depicted a linear cost function where y equals a plus bx, where y is the cost that's being predicted. So y is what we're saying our cost would be given that a is a fixed cost, b is the variable cost per unit, and x is the cost driver, or the independent variable. And so this is what our linear cost function looks like. Y is the dependent variable, the cost that's being predicted. A is the intercept, that is fixed cost. B is the slope of the line of the variable cost per unit, and x is the variable cost, or the independent variable, which is the cost driver. And so in statistics we use the same cost function, so let's just review a few of the differences in terminology between accounting and statistics. So in accounting, the variable cost is equal to a statistics slope. In accounting, the fixed cost is equal to the statistics intercept. And in accounting, the mixed cost is equal to the statistics linear cost function. And so here we see a graphical representation of the linear cost function. In the first panel, or panel A, are the variable costs associated with the use of CPUs. In panel B are the fixed costs associated with the relevant range of between 4,000 and 8,000 CPU hours, and in panel C are the mixed costs. That's the combination of the fixed and variable cost. And so again, we can see that under the panel A with the variable cost, we have a line with a slope on it. The slope of that ends up being the variable cost, and the steepness of that slope is determined by multiple factors we'll talk about later. In B, we have the fixed cost, and as you'll see, the fixed cost doesn't intercept the total cost line at 0 like the variable cost does, and that's because by definition fixed costs are fixed cost. We, from day 1 up through, or from a certain production range through an upper level production range, that being the relevant range, we have a fixed cost. And then panel C, which is the mixed cost, is the combination of the variable and fixed cost. So before a discussion of issues related to estimating cost function, it's important to review the three criteria we talked about in Chapter 2, and that is cost as fixed or variable. So the choice of cost objective. Different cost objectives may result in a different classification of the same cost. Time horizon. The longer the period, the more likely the cost will be variable, and relevant range. Behavior is predictable only within this band of activity. The most important issue in examining a cost function is determining whether a cause and effect relationship exists because of the level of activity and the cost related to that level of activity. Without a cause and effect relationship, managers will be less confident about their ability to estimate or predict costs. And a cause and effect relationship might arise as a result of either a physical relationship between the level of activity and the cost, a contractual relationship, or just knowledge of operations. We note that a high correlation or connection between activities and cost does not necessarily mean causality. And that's an important point to make, that just because we have a high correlation between a dependent and independent variable, it does not necessarily mean causality. It just simply means that there is a strong relationship between these two variables. Only a cause and effect relationship, not merely correlation, establishes an economically plausible relationship between the level of activity and its costs. So to correctly identify cost drivers in order to make decisions, managers should always use a long time horizon. Managers should follow the 5-step decision-making process we've discussed about numerous times this semester to evaluate how changes can affect cost and production decisions. And as you all remember, that 5-step decision process is to identify the problem and its uncertainties, to obtain information, to make predictions about the future, to make decisions by choosing among alternatives, and then to implement the decision and evaluate performance. And so there are several methods we can use to estimate cost, including the industrial engineering method, the conference method, the account analysis method, and 2 methods under the quantitative analysis method includes the high-low method and regression analysis. These methods are not mutually exclusive, and often more than one is used. So let's take a look at each of these a little closer. The first method is the industrial engineering method, and what is involved there is an estimate of cost functions by analyzing the relationship between inputs and outputs in physical terms. This may include time and motion studies. It's a very thorough and detailed process when there is a physical relationship between inputs and outputs, but is also very costly and time consuming. We also call this the work measurement method. The second method is the conference method. These methods differ in how expensive they are to implement, the assumptions they make, and the information they provide about the accuracy of the estimated cost function. Some of the characteristics of the conference method are that it estimates cost functions on the basis of analysis and opinions about cost and their drivers gathered from various departments of the company. The conference method pools expert knowledge, increasing credibility, and it relies on opinions, making the method subjective, though often quicker and less expensive. The third method is the account analysis method. Characteristics of this method include that it estimates cost functions by classifying various cost accounts as variable, fixed, or mixed with respect to the identified level of activity. Typically, managers use qualitative rather than quantitative analysis when making these cost classification decisions. It's widely used because it's reasonably accurate, cost-effective, and easy to use, but it is subjective. The accuracy of this method depends on the accuracy of the qualitative judgments that managers and management accountants make about which costs are fixed and which are variable, and oftentimes this is simply based on the general ledger account title. And so the next method, or the fourth method and last method, is the quantitative analysis method. This is the only method that relies on mathematics. Excel is a useful tool to perform this type of analysis, and characteristics include use of a formal mathematical method to fit cost functions to past data observations. An advantage are that the results are objective. Another advantage is that it is the most rigorous approach to estimating cost, but one of the challenges to using quantitative analysis is that it requires more detailed information about cost, cost drivers, and cost functions, and is therefore more time-consuming. So there are 6 steps in estimating a cost function using quantitative analysis of past data. Those steps include choosing the dependent variable, that is the cost that is to be predicted and managed, identifying the independent variable, that is the level of activity or cost driver, collecting data on the independent variable and the cost driver, plotting the data to observe the general relationship, estimating the cost function using 2 common forms of quantitative analysis, either the high-low method or regression analysis, and then evaluating the cost driver of the estimated cost function. So here is a sample plot of data that has been collected. This is an example of step 4 in the process of estimating a cost function using quantitative analysis. The step requires that we plot the data to observe the general relationship. We can easily observe that a relationship appears to exist between the cost driver, machine hours, and indirect manufacturing labor cost. The graph indicates a strong positive linear relationship between the machine hours and indirect manufacturing cost. Additionally, there do not appear to be any extreme observations. The high-low method is the simplest method of quantitative analysis. It uses only the highest and lowest observed values and fits a line to data points which can be used to predict cost. There are 3 steps in the high-low method to obtain the estimate of the cost function. So the first step in the high-low method is to calculate the variable cost per unit of activity. It's very helpful here to determine which data point are the high and low activity level, that is the cost driver. Note that there are 2 data points. Then for the numerator, subtract the cost associated with the lowest level of activity from the cost associated with the highest level of activity and divide that into the denominator, which is the highest level of activity less the lowest level of activity. And so if we had high activity of 100 at a cost of 2,500 and low activity of 80 at a cost of 2,100, our formula for variable cost per unit of activity would be the cost associated with the highest level of activity minus the cost associated with the lowest level of activity, or 2,500 minus 2,100, divided by the highest activity level of 100 less the lowest activity level of 80, or 400 divided by 20, or $20. So that gives us the variable cost per unit of activity. And so next we want to calculate the total fixed cost. In this step we are separating the fixed cost from the total cost. We can do this since we now know the variable cost per unit. The formula is to begin with the total cost from either the highest or lowest activity less the variable cost per unit of activity, which we just calculated, times that level of activity. So continuing our example, let's calculate fixed costs assuming both the high and low levels of activity. So at the high level of activity, we know we have $2,500 minus $20 times 100, which gets us to $500 in fixed cost, or equally so, at the low level of activity, we have $2,100 of cost less $20 variable cost times the 80 item activity level, which gets us again to $500 in fixed cost. So we have the same fixed cost in step 2, whether we use the high or low activity level. And then step 3 in the high-low method is to summarize the results into equation. Remember the linear equation from earlier in the chapter. Y equals fixed cost plus variable cost per unit of activity times activity. In our example, we would have Y equals 500 plus $20 times X, or that level of activity. If we wondered what cost would be at a 120 level of activity, we would simply plug that number X into our equation and we would get Y equals 500 plus 20 times 120, or Y equals $2,900. And so this is how we use the high-low method in order to determine a quantitative estimate. If we use regression analysis, which is a second quantitative analysis, it's a little bit more difficult. Regression analysis is a statistical method that measures the average amount of change in the dependent variable associated with a unit change in one or more independent variables. It's more accurate than the high-low method because the regression equation estimates cost using information from all observations in our data points, whereas the high-low method only uses the two observations, the high observation and the low observation. There are two types of regression analysis: simple, which estimates the relationship between the dependent variable and one independent variable, or multiple regression analysis, which estimates the relationship between the dependent variable and two or more independent variables. Regression analysis is widely used because it helps managers understand why costs behave as they do and what managers can do to influence them. And so this regression line is derived using the least squares techniques. This technique determines the regression line by minimizing the sum of the squared vertical differences from the data point to the regression line. The vertical difference is called the residual term, and it measures the distance between actual cost and estimated cost for each observation of the cost driver. The smaller the residual terms, the better is the fit between the actual cost observation and estimated costs. Some terminology used in regression analysis includes goodness of fit, which indicates the strength of the relationship between the cost driver and cost, and residual term, which measures the distance between actual cost and estimated cost for each observation. The smaller the residual term, the better is the fit between the actual cost observation and estimated costs. To make a good decision about the best cost driver, an understanding of both operations and cost accounting is happening. Three criteria are commonly used, and that's economic plausibility. So when presented with two or more possible cost drivers, each must be economically plausible to be considered. Goodness of fit, which check the residual term. Generally, shorter is better and will result in a more accurate estimate. And then significance of the independent variable. A flat or slightly sloped regression line indicates a weak relationship between the cost driver and costs. The significance of choosing the best cost driver to estimate cost is in the decisions that follow. Using the wrong driver or having misestimated costs can lead to incorrect and costly decisions. And so estimating cost driver in an activity-based costing system doesn't differ in general from what's been discussed. However, since ABC systems have a greater number and variety of cost drivers and cost pools, managers must estimate many cost relationships. They will do so using the same methods, taking special care with the cost hierarchy. If a cost is batch level, for example, only one batch level cost driver can be used. Cost functions are not always linear. A nonlinear cost function is a cost function for which the graph of total cost is not a straight line within the relevant range. And so let's look at some examples of nonlinear cost functions. So nonlinear cost functions can be created because of economies of scale, so they produce double the number of advertisements for less than double the cost. They can be due to quantity discounts. That's a direct material cost rise, but not in direct proportion to increases in quantity due to the nonlinear relationship that's caused by the quantity discount. Or we can have step cost functions, which create resources which increase in lot sizes, not individual units. Additional examples of nonlinear cost functions include learning curve. So that is a function that measures how labor hours per unit decline as units of production increase because workers are learning and becoming better at their jobs. Or experience curves, which measure the decline in the cost per unit of various business functions as the amount of these activities increase. It's a broader application of the learning curve that extends to other business functions in the value chain, such as marketing, distribution, and customer service. And so what we're saying here is that variable costs do not increase exactly as activity increases. So if we think about direct labor cost, if I pay someone $10 an hour and it takes them 1 hour to perform an assembly process, and if every hour that they work on the assembly line, if every product they produce takes 1 hour, then that becomes linear because for each product there's 1 hour incurred at $10. However, if they learn and are able to do it faster, if they have experience and are able to do it faster, then or if we can pay them overtime is another good example of this, which makes things nonlinear, so it doesn't reduce the cost like learning curves. It actually increases the cost and steepens the slope. And so you can see that there are these intervening factors that may sometimes cause a cost line to be nonlinear. And so on this chart, we see 3 panels. Panel A shows how the cost of direct materials rise more slowly as a result of quantity discounts. Panel B shows how costs remain the same over narrow ranges of the level of activity in each relevant range. Here we have units of production and setup costs. And then panel C shows a step fixed cost function. The biggest difference between B, which is step variable cost, and C, which are step fixed cost, is the range. Panel C shows that costs remain the same over a much wider range due, of course, to the nature of fixed cost. So let's discuss the types of learning curves. For many companies, learning curves and experience curves are key elements of their profit maximization strategies. They are used to reduce cost and increase customer satisfaction, market share, and profitability. Here we talk about 2 learning curve models. The cumulative average time learning curve model, which causes cumulative average time per unit to decline by a constant percentage each time the cumulative quantity of units produced doubles, or the incremental unit time learning model, which causes incremental time needed to produce the last unit to decline by a constant percentage each time the cumulative quantity of units produced doubles. In this example of cumulative average time model, the cumulative average time per unit declines by a constant percentage each time the cumulative quantity of units produced doubles. As the number of units produced doubles from 1 to 2, the cumulative average time per unit declines from 100 hours to 80% of 100 hours. As the number of units doubles from 2 to 4, the cumulative average time per unit declines to 80% of 80 hours, or 64 hours. In this example of the unit time learning model, the incremental time needed to produce the last unit declines by a constant percentage each time the cumulative quantity of units produced doubles. With this model, the 80% means that when the quantity of units produced is doubled from x to 2x, the time needed to produce the unit corresponding to 2x is 80% of the time needed to produce the xth unit. And so assuming the learning rate is the same for both models, the cumulative average time learning model represents a faster pace of learning. How do managers choose which model and what percentage learning curve to use? They do so on a case-by-case basis. Engineers, plant managers, and workers are all a good source of information on the amount and type of learning actually occurring as production increases. In this table, we see the predicted cost based on the cumulative average time learning curve. The learning model we've been discussing provide managers with information necessary to predict cost. They can also be used for performance evaluation. So now let's talk about data collection and adjustment issues, because as we talked about quantitative measures and methods to determine estimated cost, they were all based on data observation. So the data collection procedures need to be strong in order to ensure we have good data to work from. So the ideal database has two characteristics. It should contain numerous, reliably measured observations of the cost driver and the related cost, and the database should contain many values spanning a wide range for the cost driver. Unfortunately, management accountants typically do not have the advantage of working with a database having both characteristics. So let's consider some frequently encountered data problems and what we can do to overcome them. So again, here are some data problems and what we might be able to do in order to resolve them. So problem one, the time period for measuring the dependent variable does not properly match the period for measuring the cost driver. So that is, we've got observations about the dependent variable and we've got observations about the cost driver, but they're not at the same point in time, which causes the relationship between the two to be questionable, right? So the solution would be that the analyst should match the cost with the cost driver. Fixed costs are allocated as they are variable. Well, that's a problem also, right? Because the equation requires that we have a good estimate of our variable cost, and so if we've commingled fixed and variable and distorted those, we have a problem. So there the analyst should carefully distinguish fixed costs from variable costs and not treat allocated fixed costs per unit as a variable cost. So simply, as long as we can tell which costs go into our variable cost, review those and remove any fixed costs that have been treated as if they were variable from our observation points. And then data are either not available for all the observations or are not uniformly reliable. So the solution there is that the analyst should design data collection reports that regularly and routinely obtain the required data and should follow up immediately when data are missing. So to continue with a few data problems and solutions, extreme values of observations occur. So that is, we have observations that we would consider to be outliers. That is, they are way out on the top end or way out on the bottom end of their data observations. So here the analyst should adjust or eliminate the unusual observations before using the data to estimate a cost relationship. And then suppose there's no homogeneous relationship between the cost driver and the individual cost items in the dependent variable cost pool. So, and this idea of a homogeneous relationship exists when each activity whose costs are included in the dependent variable has the same cost driver. And so what the analyst should do under those circumstances is to estimate the cost separately for each activity or estimate the cost function with multiple independent variables using multiple regression. Okay, and then finally, we talk about where the relationship between the cost driver and the cost is not stationary. This can occur when the underlying process that generated the observations has not remained stable over time. The solution here would be to estimate cost relationships separately for each period before and after the change. Then, if the estimated coefficients for the two periods are similar, the analyst can pool the data to estimate a single cost relationship. And finally, a problem could be that inflation has affected the cost drivers are both, and here the analyst should remove purely inflationary price effects from the data by dividing each cost by the price index on the date the cost was incurred. And so this concludes our review of Chapter 10 on determining how costs behave. I would, again, please go back and read the text and don't let this, this lecture